Hi everyone, thank you for checking this presentation. I'm Xin Wang, a graduate student in the University of Pittsburgh. My presentation is Stacking for the Energy Prediction for Austenitic Steel, a machine learning approach aided by thermodynamic model. I would like to thank my advisor Dr. Wei Xiong and all the funding resources for the support in this work. The predicting of stacking for the energy has become more and more important topic for designing new high-strength and high-ductility alloys, and I would like to introduce what is a TWIP and a TWIP and why this is important. The TWIP means during the deformation there is a new martensite and a twin formed. As a result, the twin and phase foundry continuously refine the grains, introduce the dynamic Hoare pitch effect, and this effect can increase the strain and strength in the same time, which help us overcome the strength ductility trade-off. The stacking for the energy is a good indicator to predict if TWIP or TWIP will operate. Usually the TWIP will operate when the stacking for the energy is lower than 20 millijoule per square meter, and the TWIP effect will operate when the stacking for the energy lies between 20 to 40 millijoule per square meter. Now there are many computational methods such as empirical equations, of initial methods and thermodynamic models has been proposed to predict the stacking for the energy. However, they all have their limitations. For example, the empirical equations are usually localized for a confined composition. For example, the Rhodes believe the chromium will increase the stacking for the energy, while Bronfman and Ogman believes adding chromium will decrease the stacking for the energy. The ab initials provides a lot of detailed information. However, this is time-consuming, and sometimes it gives a negative stacking for the energy values. For the thermodynamic model, it may not be very accurate if the database is not well calibrated. As a result, we propose to build the machine learning model for predicting the stacking for the energy. First, we have collected more than 300 data, and then we evaluate the thermodynamic model and studied the influence of elements on the stacking for energy using correlation coefficient analysis. Later, we have compared the performance of 19 different machine learning algorithms using the tenfold cross-validation. And finally, we have compared the performance of the machine learning model, thermodynamic model, and the empirical model. First, let's have a look on the influence of the alloy elements. This figure represents the correlation coefficient. If the correlation coefficient is high, it means the stacking for the energy and the alloy element has a monotonic increase or decrease relationship. For example, we found the nickel has a very positive correlation coefficient, which means adding nickel tends to increase the stacking for the energy, and this has been confirmed by the literature review. In total 20 literatures, there are 17 reported the increase effect of the nickel element. How about the carbon and magnesium, which has a very low coefficient? It may have a complex alloy effect. Why? Because this carbon and magnesium still plays a moderate importance in our machine learning model, and by conducting the literature review, we find in the iron, chromium, nickel, magnesium alloy system, it do decrease the stacking for the energy, while in iron, magnesium, aluminum, silicon systems, adding magnesium will increase the stacking for the energy. Later, we evaluate the performance of our machine learning models. It can be found that the machine learning models has the lowest root mean square error compared with the empirical model and the thermodynamic model with different databases, which means it has the highest accuracy. Moreover, the errors are mostly within 10 millijoule per square meter, which is similar to the experimental errors. So, based on the analysis, we found the nickel and iron has a monotonic relationship with stacking for the energy, while the carbon and magnesium may show a complex effect. The gradient boosting algorithm performs best, and it can be used for stacking for the energy prediction and accelerates the TWIP alloy design. The detail of this work can be found in our publication, and if you have any questions, feel free to contact me.